t-test, right? So just as an overall take, right? T-test, we compare two numbers with each other. These are averages, right? But in the one sample t-test, you only have one sample, and the other number is an average from a population. So a lot of times it's a number that you get from a database, right? So for example, a teacher would see, oh, my school tested at, let's say, 100 points. Where is my class at? My class of 20 students or my class of 30 students, right? So they can compare themselves to a benchmark or standard, right? Or you could say yourself, you could say, okay, you know what? I have an IQ of 120, and if I look at my colleagues, right, their average is 120 with a certain standard error, and now you could say, well, am I more intelligent than this average or less intelligent, for example? So let me pull up the one sample t-test, and just give me a second here. So the first question you might have had with worksheet 5.3 is, all right, I get that we use a population mean, but where the heck do I get that number from? Who wondered about this? Did anybody struggle with this? Where did I get, right? We were asking about ACT scores, right? So I apologize, I kind of threw you in there for a loop, right? But the thing is, all this information is on the internet, for example, right? So these days, it's widely accessible. So you could think of it this way. Any test you take that is widely published should have some norm references that you can relate to, right? So you can look them up online and figure out, well, what does my individual score mean in the context of things? All right, let me jump in here. All right, so you should see my Excel spreadsheet. Does everybody see that? All right, great, thank you. Okay, so first step is this, right? We have group 1 and group 2, but now we don't worry about which group they're in. They're both students of Miss Hernandez, right? She has 2 classes, so these are all her students. So what we do first is we have all these individual scores, and we calculate the average for the class, right? So the average is all these scores divided by n, gives us a score of 24.75. That's the class average. And now what we do is we calculate the standard deviation from that, right? And as you know, we do this by subtracting or by calculating the difference between the individual score and the average class score. So in this case here, right, this person has a score of 26. The class average is 24.75. And so if we do x minus the class mean, we get 1.25, which means this person is 1.25 points above average. Okay. If we go to person 3 here, the third person, we see it had 21 points. And that means if you look at the class average of 24.75, this person was 3.75 points below average. Okay, so you get the picture. You do this for every student. Then in this last column here, we square this difference, right? That way we get rid of the negative values, right? You see minus 3.75 becomes 14.06. And also by squaring it, we do punish bigger differences from the mean, right? If you're farther away from that average and you square that number, it becomes much bigger, right? So let's say 1 squared is 1 times 1 is still 1. 2 squares is 4. 3 squares is 9. 5 squares is 25. So you see how the farther away they are, if we square it, they're even further away. So we kind of exaggerate the differences. Then we add all these differences up, and we get this sum of squared deviations. And the sum of squared deviations, we use this to calculate the variance. So the variance, and you can see now I'm going to explain a little bit the Excel, right? You see that's cell E28, that's this blue cell, divided by 20 minus 1, right? Divided by n minus 1. That gives us the variance. So the variance is...
Dr. Wandeller?
Yeah.
Question. When would you divide by n minus 1 and when would you divide by n?
Thank you, Alex. So there's other people that asked this question as well. So in statistics, we tend to divide by n minus 1 because dividing by n minus 1 gives us a bigger average variance. So that's big. We are trying to generalize from the sample to the population. So we're trying to kind of overestimate the variance, not underestimate. And if you recall in worksheet 1, right, we did divide by n as a descriptive variance and divide by n minus 1 as the inferential variance. Right? And then we also said descriptive standard deviation or inferential standard deviation. So that at this point in time, I didn't mean to confuse you guys, but that way you really understand where this is coming from, right? You can think of this variance as an average deviation, right? Divide by n, same thing as calculating average, but now we use n minus 1 because we're doing a statistic. So we're estimating the population variance with the sample. But because we know that the sample tends to be less varied than the population, we kind of give us a little room for error and we expand that a little bit. So n minus 1 gives us a bigger number. Did I answer a question?
Yes.
Okay, great. Does anybody else have a follow-up question to that, or was that clear for everybody? So from now on, whenever you have to calculate a standard deviation or variance, it will be n minus 1. For the mean, we use n. For standard deviation, we use n minus 1. And then here, the standard deviation, I just did the square root of the variance. Okay. So I did all this here, this whole thing, just to show you guys where it's coming from, right? You did that all by hand in the first worksheet or the second worksheet. And here you see what Excel does in the back. Now, I want to show you in Excel, you could go directly to the standard deviation, right? And I made it a little bit more explicit in the other examples for the homework in worksheet 1 and 2. I showed you exactly which standard deviation formulas we have in Excel. But here, if you say stdev as the command in Excel, and then you can say the range, this blue field here, right? You could highlight B towards B2 towards B21. That gives you the standard deviation. So this is a short form for all the other stuff that I did here, right? So you don't necessarily have to do all this. This is just to really make it explicit and for you guys to see where it comes from. Any questions so far? So now we would have the mean of this sample and we have the standard deviation. So that will be the main thing, right? And then we know n is a sample size of 20. We know how many people are in this. Can you guys see the size of the font in this spreadsheet? Can you see it all right? All right. Okay, so here on top, we have the formula. So what I'd like you to do right now at home is complete this formula here. complete this formula for the one sample t-test with the numbers that we just calculated. So I'm going to go over here and I'm going to try to scoot this over so that you see both of them. So I'd like you to plug these numbers into the formula. Can you guys see the numbers and the formula? Does it work all right? So we have here X bar, the mean, right? That's the sample mean. I would take 24.75. And mu, right? Mu is the average of the population, right? Mu, we use a Greek letter for the population. And now is the tricky part, right? Which one should we take? And I'll get back to that. So we'll plug in here the mu. And on the bottom, S stands for the standard deviation. We plug in the 519 for the standard deviation of the sample. Then the N, this N here, we complete with the 20, right? So now we have, all this is information from the sample. What we're comparing it to is the population. So here is the tricky part, and I did it now for all the scores of the ACT from 2012, 2013, and 2014. So if you want to practice the one sample t-test, I suggest you use these different numbers here, and that will help you complete the, practice the t-test, the one sample t-test. So, all right, here we have in 2012, we had a population mean of 21.1, and our sample here is 24.75. Right? Now, we're plugging this into our formula, right? And I had this plug in up here. I said, okay, 24 is the sample mean, the difference. And then here is the, Here, the blue is the difference, that's on top. And then we go divide by the standard deviation and the square root of n, 20. So that gives me the t calculated. Okay. The p-value, remember how there is these distribution, these curves. The p-value you can get in Excel with this function. TDIST, and then you enter the t-value that you calculated, the degrees of freedom, and if it's a one or a two-tailed significance test. And if you have questions for the Excel commands, you can click on here and a help window will pop up. Right, so I get this, so here's the help window I was talking about. Let me put this away right now, we can look at it later. So we calculated t-value of 3.15, and now we're curious about, well, what's the probability of getting this value, right? We're wondering, imagine again, imagine the normal distribution. It's not actually normal, it's a t-distribution, but imagine this two-tailed distribution, and you're wondering, well, is it really far away from the middle, or is it close to the middle, right? So we say, hey, if it's far away enough from the middle, we're going to start rejecting the null. If it's close to the middle, but it's not exactly zero, but it's pretty close, we say, you know what, they're pretty similar. We're going to retain our null. We're going to say there's no difference. So if we're testing at the 5% significance level, what would you guys conclude here? A t-value of 3.15 and a p-value of 0.05. what do you guys conclude? Would you retain the null or reject the null? So Susie is saying we reject. Who else is saying we reject? Jack, Kara says reject. Everyone should be saying reject the null, right? You see that the probability of getting this t-value is 0.005, right? It's a very small probability. It's smaller than 0.05. So, Alex says exactly right. If we test at the 5% significance level, that means that as soon as the chance of obtaining such a p-value is smaller than 5%, we reject the null. Right? Imagine these two curves. It's so far away from zero that it's very unlikely to get such a value if there really is no difference in reality. Right? Sometimes you get a value like that when there's no difference, but it's very rare. So if we see that, we are going to change our hypothesis because it's very unlikely to see that. So I want to go back real quick. Susie's asking a good question. Why aren't we using n-1? Shouldn't be 19 on the bottom and not 20? Okay, good question. Now here it is just based on the formula. The formula for the one sample t-test is S divided by the square root of n. So that's what the formula is, and that's why we divide, why we use the n. On the other hand, we use for the degrees of freedom, we use n-1. So for the degrees of freedom, we use 20 minus 1, so we get 19. And then there's another way to do it, right? We answered our question with the p-value, but all right, you remember there's the second way is to define the t-critical, right? Where those darker zones start, where the zone of rejection starts. And then all you wonder really is, does the value go over the this barrier in the sand or not? And if you go that route, we used to always go that route before we had computers, because you could publish tables in a book that would tell you, this many degrees of freedom. Here is the limit of the zone of rejection, right? This is where the T critical is. And you just figured out, am I above the T critical or not? But now that we have computers, we can give us precise values. We know exactly where we're at on the curve. But if you had a table, you could look this number up, or you could use this function here in Excel, TINV, and then we specify the probability, right? Here we test at the 5% level, so it's 0.05. If we test it at the 1% level, it will be 0.01. Okay? And then we add the degrees of freedom. Right? So each degree of freedom, each sample size, each degree of freedom has a different t-distribution, a different curve. And then we can figure out where is the 5% value on each of these curves. So either way is fine. You don't have to do both. Either way is fine for me. I would probably go with figuring out the p-value because it seems a bit more precise. And all you really need to know is, hey, which significance level do I test at? The 5% or the 1% or the 0.01%? And then figure out, well, is this p-value bigger than my significance level or not? right? If it's bigger than my significance level, I retain the null. If it's smaller than my significance level, I reject the null. All right, so this was basically the one sample t-test. Any questions, comments? Let me see. All right, so Susie says she's confused. When do we use n-1? When do we use n? So we use n-1 to calculate the standard deviation, right? So that will be in this first step where we calculate the standard deviation. To calculate, let me go over here. To calculate the t-test, that's something else, right? So here, to do these calculations here, right, to get the standard deviation, we use n-1. And really, to be honest with you, if you use this function here in Excel, you don't really even know about that, right? You don't have to worry about it. You just use this function and then it does it for you. But what you're referring to here in the t-test, right? This is this big formula. That's independent of, like here you use n, right? That's something else. The n-1 was actually flowing into the standard deviation calculation, right? That's where we use that n-1. I hope that was that okay. That should be clarified. Okay. Alice asked, do we always test at 0.05 unless otherwise stated? Yes, that's correct. So in this class, and we talked a little bit about it, right? In social sciences, we conventionally use 5%, 1%, or 0.1%. And those are just conventions, right? There's no rational, we could say 4% or 6%, doesn't really matter. So if I don't say anything else, we'll test at the 5% level. All right, are you guys ready to move on to the paired samples t-test? Well, let me think. No, let me do this. I'm going to start with the independent samples, because the paired samples is basically the same as the independent samples. There's just a little bit of a difference. Okay, there's a little bit of twist to it. Right, Brittany, when the p-value is smaller than oh, and guys, if you haven't downloaded, you can use the formula to calculate the mean. You can use the formula to do the standard deviation, right? You can use these simple formulas here. You can plug them into the formula for the one sample t-test, which gives you the calculated t-value. And then you can use a formula, the t-dist formula, to calculate the p-value. And then you have all the necessary information to answer the question. Okay. So sorry about that. I thought this was easier to use than anticipated. All right, let's look at the independent samples t-test. So in independent samples, we have two samples with different people in them, right? So that's the main difference between independent samples and paired samples. In paired samples, you have the same people twice, or the same units twice. In the independent samples, there are different people. So here, I did basically the same thing in the beginning, right? I show you guys over here how we calculate the standard deviation. I'm gonna go over it really quickly. Same principle, right? We have group 1, and then we have the individual test scores for group 1. Out of these individual test scores, we calculated an average for group 1. And then we calculate this average for each of these individuals, right? It's the same one. That's the whole group here. Then for the group 2, that's a different one, right? So this is the average for group 2. So this 22.6 is the average of all these individual scores for group 2. Then we did the same thing. We looked at the difference of the individual to the group mean here in this column x minus x bar. And you see that, let's pick somebody that has the same score. They're all different, but let's say here this person is 21, right? Is minus 5.9 points below the average. This other person is 21, it's 5.9% points below the average. And if you look at this person here, 22, well, this person is, scores similarly than these other two, but because the average test score in group 2 is really lower, that person is only minus 0.6 points below the average, right? So anyways, these different scores are in relationship to the group averages. Then we do the same thing. We square this difference, right? So minus 0.9, it becomes positive 0.81, right? You see that a negative goes away, plus the squaring, if the number is below 1, the number becomes smaller. If it's above 1, that number becomes bigger, right? So let's go here, minus 5.9. Wow, that becomes a 34 points difference, right? A huge difference. The 4 is a 16-point difference. Yeah, it's pretty big. But then if you look at a 2, that's only 4 points. 7 is a 50 points. So you can see how if they are a little bit further away, they get even more further away when it's squared. If they're closer, they get even closer. So 0.4 becomes a 0.16. So I'm going to zoom out just a little bit. All right, so here's same concept. We add up. That's the sum of the squared differences of group 1. And we take the sum of the square group differences. And now here we go n minus 1, right? Because we're calculating the variance, we're calculating the standard deviation. That's why we do it. And then the variance, the square root of the variance gives us the standard deviation, or conversely, the standard deviation squared gives us the variance. All right, so now if you did that, you would have the standard deviation for group 1. And we can do the same thing to get the standard deviation for group 2. If we did it the short way, we could just type in standard deviation for the area B2 through B11, and poof, we would have the 4.56. Let me expand this really quick. Because of rounding, it's not the same, but if you see, if I take that away, it's the same exact number. So if I hit equal and I select standard deviation, and then I open the parentheses, I say, okay, we want to have the group 2. I select the area that I need for group 2, close the parentheses, hit enter, and now it should calculate this. I don't know why it doesn't do this, so we once in a while you gotta be patient with it. All right. So now this is still the top area. I want to drag this down. I want this area here. All right, 5.08. So that's the standard deviation for group 2. So now we have all the necessary information, right? If we look at the formula for the independent t-test, we need sample size, the average for group 1, x bar 1, average for group 2, x bar 2, and then for the term under the bar, the line here, we need standard deviation for group 1, n of group 1, standard deviation of group 2, n of group 2. Now, if we plug this into our formula, we get the t-value, and the calculated t-value for this would be 1.99, right? So I created 2 points here. This is the difference, right? That's 26.9 minus 2.6. That's the difference in mean. The bottom, we have this pooled variance. This is the formula that calculates the term underneath here, right? So it's the square root of standard deviation 1 squared divided by n plus the square root of standard deviation 2, the standard deviation squared, the standard deviation 2 squared divided by 10. So standard deviation 1 squared divided by 10, standard deviation 2 squared divided by 10. We add these two, and then we take the square root of both of them. And then we divide this difference here on top, divided by the term on the bottom here, gives us the 1.99. And now what we can do is we could calculate the t dist, right? Or what we could have done, if we only wanted the p-value, we could have just said, you know what, Excel, please calculate a t-test, right? So t.test, and we could have said, okay, Excel, here the blue area is the group 1, the green area is at group 2. This is what this here is saying. Blue area, green area, and then we would have said, well, here is it's explained. It's a one-tailed test, and then you could say, is it an independent or a paired samples or independent samples? In this case, you see type 2, right? Here's the type 2, and that means it's a independent test. So here we have the probability for independent tests. Now I would like to take a vote. So right, we did all this trouble. We calculated t-value. It's 1.99. Now the question is, right, if you did imagine just distribution, 0 is here. It's 1.99. Or it could also be negative 1.99, right? Same probability. And we learned that the probability, the one-tailed probability to obtain such a value is 0.03. So imagine we had a one-tailed hypothesis. We had a directional hypothesis. What would you guys conclude? Would you retain the null or reject the null? Would you retain the null or reject the null? The probability is 0.03. Reject. Yes, reject. What would you do if you had a two-tailed? Well, if you had a non-directional hypothesis, if you would test the two tails, and you can see here, if the two-tailed, it would be 0.06. What would you do then, guys? Would you reject the null or would you retain the null? Right, so you can ask yourself, well, okay, the significance level is 0.05. Is it bigger than the 0.05 or smaller? Okay, here we see it's bigger, 0.06, so we retain the null. Right, and the reason is why we retained it, we tested both sides, so it was really right on the edge, right? So when you test both sides right on the edge, but if you test only one side, you get that 2.5%, right? If you two-tailed, you have each side, you have 2.5%. If you go one-tailed, you get that 2.5% on this side as well, so the probability increases, right? That whole area on this side becomes bigger. So now it's really pretty much in the middle of your dark area, whereas before it was right on the edge. So here you can see how important it is to have a good hypothesis. So if you have a good hunch, if you think, oh, it's going to be higher, it's going to be lower, do formulate a directed hypothesis. Directional hypothesis gives you more power, right? Statistics rewards you for having a good hunch. And here again, so you can either calculate the mean, right? You can use this formula. You can calculate the standard deviation, use this Excel formula. It goes really fast. And then you can plug this into this t formula, which gives you the t-value. And then with the t-dist function, you could figure out the probability. But for this class, this won't be enough. But if you just wanted to know what the p-value was, you could do this t-test here in Excel. But that only gives you the p-value. It doesn't give you the actual t-value. So for the purpose of this class, this shortcut here won't quite work. And then if you use the real statistics, you can create this output here. And you create this output by going into, on the top menu on the very right, real statistic, data analysis, the t-test. Now here again, the input ranges. So we have to say B2 through B11, that's group 1. And then B12 through B21, that's group 2. Then again, I'm going to uncheck column headings because I didn't do that. Alpha 0.05. Now I have to decide.
We can't see your screen.
Oh, yeah. Thank you for letting me know. Let me see this. Does this work? Now you should see. So here what I did, I entered B2 through B11 in the top, B12 to B21 on the bottom. So this, the top is the first group. The B12, B21 is the second group. I unchecked this column heading. I entered 0.05 for the alpha. And then I hit the 2 independent samples as the t-test. Now you can specify the output. I'm going to change this. I'm going to say I want this at B74, so it should write it right underneath that existing table that I have here. So we hit OK. Okay, and I'm going to share my Excel screen. Let's go here. Can you guys see that all right? All right, now you see here, okay, it added this whole table underneath, right? So it calculated the means for each group, it calculated the variance, which we can get the standard deviation standard from. And now here, okay, the t-value 1.99. So we did a good job. We got the right t-value. See degrees of freedom 18, and then the p-value 0.03. Now you can see a two-tailed test, you have the same t-value, right? The t-calculate doesn't change, but the p-value changes, right? Because we tested, in the one-tailed, we tested one side. In the two-tailed, we tested 2 sides. You can also see it from the t-critical, right? T-critical in the one side is closer to 0, and t-critical in the two-sided is further away from 0. And this table even tells you is it significant or not. Right? And you can, let's think about this really quick. How does Excel know this? Well, if you look at this formula here, it's a logical test that says if 84, the cell 84 is smaller than the cell here, 0.05, then write yes. Otherwise, write no. Right? So that's basically what you can think about. Well, is it smaller than 0.05 or not? If it's smaller than 0.05, yes, I reject the null. If it's bigger than 0.05, I retain the null. So it's here yes, and then in the other case, no. So this will be the independent samples t-test. Questions or comments? All right, who feels confident about the t-test, the independent samples t-tests? See some of you shaking heads, some of you giving a thumbs up, right? If you feel like, it helps a little bit, but not quite, you know, do another practice run. I'll be probably doing another session. Well, post question on this discussion board. If there's a lot of questions, I'll do another session before Thursday. Okay. All right, so let's go over to the independent samples the dependent samples t-test. Sorry. So what's the difference? I would like you to post in the chat. What's the difference between independent and dependent samples? What's the difference? We have two groups in both instances. So what's the difference between independent and dependent samples? Susie's saying whether or not the group is made up of the same sample or different samples. Yes, so the people or the units are the same in both samples. All right, you can say it's the same group before and after, or the same group, for example, in English and in math. All right, so that's what the difference is. And you could notice that as also in the way that we set up the data set. So I should be sharing you should be seeing my Excel file again. Do you guys see that? All right, cool. Now you notice here, I just have group 1. Right? There's only one group, but we have a pre-test ACT, and then we have a post-test ACT. And, you know, for the example here, what I did is I kind of pretended that this was the same group, but really what I did is I just copied the numbers that were down here that were group 2. I put those numbers over here and pretended that now this would be the same people. Okay, so just bear with me, okay? So I faked that we did it with the same people twice. So imagine this is before the people take a Scientology course that increases their intelligence, and this is afterwards. I'm just saying something. Or this is before they take a Red Bull, and this is afterwards. And now we can do the same thing, right? We have the individual scores. We calculate the group average. We calculate the distance for each individual to the group average. We square these differences. And then we add up these square differences. This gives us the sum of the square differences. We can divide that by n minus 1, which gives us the variance. And if we square, the square root of variance gives us the standard deviation, right? So these numbers should look really familiar because they're based on the same individual scores that we used earlier, right? And now we do the same thing for the second group, and these numbers, again, are the exact same thing that we did earlier. And now what I did here, I did a little calculation and showed you the different SPSS formula, Excel formulas. So here we're using the STDV.S formula to calculate the standard deviation. This is the one that we want. That's a sample standard deviation. Now, if you only hit STDV, this one here, you get the same result. Right? So by default, if you want the standard deviation from SPSS, it will use the statistics formula. And I want to share you a little anecdote. About 10 years ago, I worked at a test center in Switzerland for athletes in sports psychology. And I had a doctor that came to me and said, you know, Christian, help me out. My Excel is not giving me the right numbers. And he said, man, the standard deviation is always different. And I was like, well, I don't know. I didn't know what the heck was going on, right? And what we finally figured out is that he was using the formula divided by n to get his standard deviation, whereas Excel was using the formula n-1. Right? So here a little anecdote about that in statistics, we want to use the inferential formula, which is this. And then you can see here the standard deviation .p, this formula. Here we actually use the divided by n formula. Right? Why would we do that if we want the population standard deviation? Why do we only divide by n? Right? I said, hey, when we do statistics, right? I said earlier, from now on, we're always going to do n-1 when we do statistics. Now I'm talking about, well, the population standard deviation formula here is divided by n. Why do I do that? I do it because we know now, right? If we know if we do the statistics, we're doing n-1 because we want a little bit bigger standard deviation because we're trying to guess the population, right? But if I know already the population, I want to be exact, right? You know everybody, so you can do divide by n. Right? We use statistics to guess the population, but if we know the population, there's nothing to guess. We know what we're talking about. I imagine if you asked 100 students of Fresno State, you would divide by n-1. If you use every single of the, maybe 24,000 students, you would divide by the sample size, by the population, right? Because we're not guessing. All right, this is just a brief explanation of where these numbers come from. But here, basically, we have almost all the components, right? We have the mean of the group one, or pre-test one. We have the mean of the post-test. We have the standard deviation. We have the standard deviation of the post-test. What are we missing? All right, we have all this, but we're missing this piece here, specifically this R12. Right? And I didn't say a whole lot about this R12. What is this R12? Anybody recall what this is? The R stands for correlation. And the correlation is a measure of how similar scores are in both groups. And the correlation you can calculate by using an Excel formula. You can see correl, and then we say, okay, the blue area, group measurement 1, pre-test, with the green area, post-test. So we correlate these two scores with each other, and we get a value of 0.19. A correlation can go from -1 to +1, and I'll say more about that when we get to calculating correlations. But for right now, we just want to calculate it, and we use it as an adjustment for how similar these values are. Because since we have the same people twice, we want to leverage that for our calculation. Now, I want to point something out to you guys really quick. Let's imagine that these two samples are unrelated, which would mean a correlation of 0. There's 0 relationship. And if we would plug that 0 into this formula for the dependent t-test, right, we would get 2 times the correlation of 0. So 2 times 0 is 0. Then 0 times the standard deviation is 0, right? 0 times 5.08 is 0. 0 times 4.56 is 0. 0 divided by 10 is 0. So it would be minus 0. So that whole portion here of the formula would fall away, right? So if there is a 0 correlation, this whole portion falls away. We are back to the formula for an independent t-test. You guys see that? So if there's no relationship between those two groups, it's basically like they're not even similar, so it doesn't even really matter that you have the same person twice because it didn't relate at all. It's like they're strangers, right? So then we're back to using the formula for independent t-test. Any questions about this one? All right. So now what we do next is, again, we calculate the mean difference. So here's the same thing that we had already. And then what we also do is we calculate the bottom variable here. And now it's the same thing as we did for the dependent t-test, for the independent t-test. The only thing is we added this term here, right? So it's the standard deviation of group 1 squared divided by 10, standard deviation of standard deviation of group 2, well, which here is the post-test, right, squared divided by 10. And now we subtract minus this term here, minus 2 times the correlation times standard deviation of the pre-test times standard deviation of the post-test divided by 10. And to get the t-value, we calculate the top, the mean difference, divided by the pooled variance, this term here on the bottom.
Question?
Yep.
On the formula, you're adding the last term?
Oh, thank you. Who is this?
Alex.
Thank you, Alex. This is awesome observation. So please, okay, here it's right and here is wrong. So let me make sure that you download this again if you downloaded already. So I'll upload this. Maybe wait a few minutes after we finish this broadcast so that I can upload the right version. So now what we have is we have a t-value calculated, and from here it's the same principle again. Either you calculate the probability with the dist formula, or you use that t-test formula that's incorporated in Excel. But here again, the problem is it only gives you probability. But I mean, I guess that's better than nothing. And here again, you have to choose, well, tails, one tail or two tails, and then type. Remember how type earlier in the independent t-test we had 2? Now we have 1. So this is the formula for a paired samples t-test. And you can see the one-tailed significance is 0.027, right? Earlier it was 0.03. And the two-tailed is 0.53, right? So you can see how the this t calculated here is a little bit smaller than it was before, right? And the probability level went down a little bit. So what would you guys conclude if you did a one-tail test? Would you say that the test scores from pre and post, did they go up significantly? If you did a one-tail test, would you say yes or no? All right, you could ask yourself this question. Is it smaller than 0.05? Or is it bigger? And Kara says it, well, reject the one-tailed and retain the two-tailed. All right, so in this case here, one-tailed would reject the null. We would say there is a significant difference. Two-tailed, we retain the null. Barely, right, by a hair, but that's the game, right? We say, hey, this is where the line in the sand is, and if it's bigger or equal than 0.05, we reject. We retain the null. If it's smaller than 0.05 or equal, then we reject. Now, yes, you can maybe wonder how often when you have a result like this, 0.053, and you say, oh, I'm not going to reject the null, how often actually should you reject the null? All right, so that's what we call the type 1 error. When you fail to reject the null, although there will be a difference. And opposed to that is the type 2 error, when we retain the null, but there is a difference. So let me use the real statistics, and I hope that goes a little bit smoother here. So the data analysis tool. T-test non-parametric, I hit OK. Now we want to say, okay, which ones of these do you want? And because this is really weird, I don't know if you guys can work it, but I'm gonna come up here so that I actually see what I'm doing. Did you guys see what I'm doing? Right, I want to say the first group over here, B2 through B11. So I'm going to tape them in, B2 through B11. Then the second group is over here, F2 through F11. F2 through F11. Then I don't want the column headings. Now I change it. I'm going to say it's a 2 paired samples. And the output range A53, that was down there where I was earlier. And I think it's all is good. I hit OK. Let's go look. All right, great. It entered for group 1, 22.6, group 2, 26.9. So keep in mind, right, these two groups is really the pre-test and the post-test, right? Same people in these groups. You see the difference, 4.3, and the T calculated minus 2.225. Let's go look up here. Do we do it right? T calculated minus 2.225. All right, we're good. And now we get the probability, right? P-value 0.026 for one-tailed and 0.53 for two-tailed. Then you also get the result here. Yes, for the one-tailed, we reject the null, and no, for the two-tailed, we retain the null. So this was the paired samples t-test. Questions about the paired samples t-test? No questions. Comments in general, questions in general. So for this week, what I'd like you to do is just practice some more. and the exam 1 will be going on from Thursday. I'll open it up on Thursday till Sunday. It will be available. And you're going to have 3 hours. Whenever you want to do it, you can do it, right? It asks you not to share information with each other about the test, right? That's just, I want to make sure that you are comfortable, that you can schedule it when you feel like fits in your schedule. But I just ask you not to share information with each other. And then what I will also do is I will probably, on Friday, I'll probably already release the next module. And you don't have to get started on it right away, but I just want to make sure that if you do have time this weekend and you had to took the test already, that you can get a head start, that you can start working on it. Okay? So I just I'm trying to accommodate whatever you guys' schedules are, and then we'll really officially start on Monday with that. Let me see here. There's some questions. Is there going to be a practice test? No, there won't really be a practice test, but I have to say that a lot of the questions I have on there are going to be similar to the quizzes that you guys took. And then there's questions that are going to be similar to the worksheet 5. So 5.1, 5.2, and 5.3, what we've been talking about tonight. There won't be all of the t-tests, but there will be 2 of the t-tests will be on the exam. Okay. Yeah, so Kara, yes, it's going to be like the worksheets we have had so far. And then okay, Jorge would like to know how to get the correlation, or R1, R2. So I'm going to show you guys that again. And really, for the test, what I encourage you to do is, if you understand how these worksheets come about here, you should be fine. So you can just adapt these worksheets as well. Click on the formulas, understand how the formulas come about. There's also these Microsoft Excel tutorials on lynda.com, which is really awesome, which are, to be honest with you, some of them are overkill, right? There's a lot of information there. But as far as preparation in the workforce to get jobs and things, Excel is a great skill to have. So in my opinion, you can't go wrong. And, you know, maybe it's actually a good thing that we weren't able to have access to SPSS. All right, how do you get the correlation? You have this formula here in Excel, which is called Correl. So C-O-R-R-E-L. And then you have to indicate the 2 ranges. So that group 1, B2 through B11, and group 2, F2 through F11 in this instance. So basically I have to tell it, okay, there's this group of values, and then there's this other group of values, and I want you to figure out how are they correlated. And you could do it by hand, right? I'll show you guys how to do it by hand, but you don't want to go there right now. Is there a question? Comment? So for right now, just trust me with that, or better, trust Excel. It will calculate the correlation for you, and then you can plug it into the formula. All right, comments or questions? Did that answer your questions? Jorge, was that good? All right, cool, thank you. The test is not timed. The test, you just have 3 hours to do it, and it should take, I would say, about an hour and a half. And there will be a lot of multiple choice questions. You know, that should give you some hints as well, gives you some idea. You know, if you have a number that's not even an option in the answering sheet, that gives you a hint as well, right? But yeah, to be honest with you, I selected 3 hours so that nobody runs out of time. If you do run out of time, that would mean as well that let me just say it this way. If you do it all by hand, you're probably going to use the 3 hours. If you're going to use the formula that in Excel that we discussed tonight, like the shortcuts, you're probably going to you might not even use an hour, right? But I don't want you to feel time pressured. So I think 3 hours should be plenty. Yes, Kara is asking, will there be multiple answer questions or is there one answer for each question? No, important point. There can be multiple answers for each question. Now, I'll give you this. A lot of times it's just one, but there can always be 2, 3, or 4 or more. Right? That's just to keep you guys on the edge. You'll have to type in numbers once in a while. If you do have to type in numbers, I will specify the format exactly. Okay, and then you have to round. Let's say if there's 2 digits after the comma, then I'd ask you to round to the second digits. If there's 3 digits after the comma, I'll ask you to round through the third digit. So basically, p-values, I'll ask you to indicate 3 digits. Standard deviation and means, I'll ask you to indicate 2 digits. And that's APA standard practice as well. So that's why I do it that way. So what I'd like you to do is, if you have other concerns or questions that come up, maybe let this sink in. Maybe I'm going to post the link to this video. If you want to look at it again, hopefully it's been useful. If you have other questions, let me know. I will be available to Tuesday, Wednesday, and then if there's a lot of people that have questions, we might do another session on Wednesday evening. All right. If there's no other questions, I would say have a great evening. Thank you for coming tonight, and I look forward to seeing you again either Wednesday or next week. All right. Have a good evening, guys.